Hi everybody. In this lesson we're going to talk about vectors, how to add and subtract vectors mostly. So vectors, as we know, are a representation of magnitude, that means how much it is, as well as direction. And so we use a vector for that, an arrow for that, to show those things. So the direction, obviously, when we have an arrow can show us direction, and then the length of the vector is going to tell us the magnitude of it. And so when we add these together, we're going to talk about those things, about magnitude and direction. So vector arrows may represent any vector quantity, and we're talking about displacement, comma, velocity, acceleration, force, anything. Anything that is a vector quantity can be represented by a vector arrow. And the magnitude or size of a vector is shown by its length. So that's kind of what we were just talking about. When we add and subtract vectors, a couple of rules. We always add vectors tip to tail. The arrowhead shows the direction of the vector. So, for instance, I have this diagram over here. This is a vector. And when I add these together, I'm going to add them, like I said, tip to tail, where like the tip and the tail are going together. You never put the two heads together or the two tails together. When we add these together, we call that sum the resultant vector. So for instance, I might call this vector A, and when I call it vector A, I usually put a vector arrow over it. And this might be vector B, and I have an arrow over it. And then if I add those together, then what I get is the resultant vector. And so if we think about this like kind of in an everyday example. So maybe you walk across the street to your friend's house, and then you kind of cut through the yard and you go to someone else's backyard. How far did you walk in total? And so this resultant vector is how far your displacement essentially is your displacement, how far you walked altogether. Okay, so that sum of the components is equal to the resultant vector. So this is component A, this is component B, this is the resultant vector, and that's an R there. A negative vector is one that has the same magnitude but opposite direction. That is 180 degrees difference. So these two vectors are opposites of each other. So I would say this one might be a positive vector and this is the negative vector. So they're exact same length, but they're pointing different ways. And when we subtract vectors, I might call that so I'm going to go back and say that this is, for instance, vector C. Well, then this is negative vector C, all right? And when we add or subtract vectors, we typically add them, but sometimes we do subtract them, and if we subtract them, it's like adding the negative. So just like when we have numbers that do this. And we'll look at a couple of examples of that. So one way that we typically use to help us add and subtract vectors is by using what's called a graphical method. In other words, putting these on a graph, on a coordinate grid, so that we can add and subtract them a little bit easier. And so when you do that, you need to choose a convenient scale and choose convenient coordinate axes. The scale is just, when it says convenient, if we're talking about miles, then let's make it miles. If we're talking about inches, let's make it inches. And then whatever axes you want to do, north, south, east, west, or 0, 90, 80, 270, or x and y, or whatever makes sense in your situation. And then typically when we do this, we're going to rely on our trigonometry because I'm going to go back up here to my diagrams. You can see we've got some triangles, we've got some angles, we might use some trig to find out some of those missing pieces. And so we might use the trigonometric method. And to do that, we have to break our vectors into x and y components. This is going to be big for us. We're going to be doing this a lot. Add all the x components and add all the y components, and then use the Pythagorean theorem to find the result. Okay, so let's do some of these examples. That's supposed to be example 1. If you walk 25 meters north and then 15 meters west, what is your displacement from your starting position? Well, we talked about having a convenient scale, and unfortunately my graph paper here is not convenient, but we're going to do it anyway. So let's just say, for instance, let's say this is your house down here. You're going to walk 25 meters north, so that's 10, 20, 25 meters, and then 15 meters to the west. So by using the same idea, then this will be 10 more meters, and then we're going to go over to 15 meters. So we go 25 meters north, we go 15 meters west. The question is, what is your displacement from your starting position? Well, for displacement, we're going to have a resultant vector. Okay, not the most beautiful, but there's my resultant vector. hopefully you would use a straight edge for that. So you've got a nice triangle here, but I think we can see that we're going to use the Pythagorean theorem to find out what that resultant vector is, because north and west are obviously at a 90-degree angle from each other. So let's go ahead and start the Pythagorean theorem here. Okay, so I do my Pythagorean theorem, and I get that r, the resultant vector, is 29.15 meters long. So that's your total displacement, is 29.15 meters. Now, another question might be, what angle is that at? And so that's something else that we do need to consider. And so going back to our trig, we need to think about, okay, what angle is that, and how are we going to describe that? Because we could describe it from this direction, or we could describe it from this direction. I'm kind of inclined to use this one. So to do that one, that's going to look to me like a tangent. So for instance, let me draw in if you're not following me here. So let's say we've got this triangle. So we would know that the tangent of theta is opposite over adjacent. That's 25 over 15. So if we go to our calculator and take 25 over 15, so on your calculator what you do for this is you want to take the inverse tan, because you already know your ratio. So you're going to take the inverse tan of 25 over 15. And you can just do that in one step on your calculator. So you do the inverse tan of 25 over 15, and that gives you theta, which is 59 degrees. So that angle is 59 degrees. Now, if you did want the other angle, you would just take 90 minus 59, and that would give you this one, which would be 31 degrees. And so when we give our answer, we want to give our answer in terms of both the distance and the angle. So our solution is going to be that it's 29.15 meters, we know that. And then the description, we have these maybe different than what you've seen before. I'm not going to call this northwest. I'm going to say it's west of north, because the north would be this straight up and down, right? And so if I compare that with the north, I'm going to say, well, it's a little bit west of north. Another way to say it is you could compare it with the horizon, and you could say it's 59 degrees north of west, right? If you're comparing it to this horizon, then it's 59 degrees north of west. It's, or maybe you would describe it this way. There's a bunch of different ways to do it. And in fact, right now, I think for us, this might be the more obvious way is this 31 degrees. Okay, let's look at another example. A plane flies at 100 meters per second north with wind blowing at 28 meters per second to the southwest. What is the total velocity of the plane as seen from the ground? Okay, in this case, they are talking about southwest, so that is going to be exactly the 45-degree angle. That's the one time that we could use that kind of a word, is if it was exactly at 45 degrees from whichever direction. All right, we need to think about how to set this up. I might make my increments here, 25, 50, 75, 100. So I've got my full vector there at 100 meters per second north. Notice this is velocity. It's meters per second. It's not distance. So yes, it's an arrow, and sometimes we kind of in our brains we think that these represent distance. It doesn't. It represents velocity. It's velocity going that direction. We can represent that with an arrow, with a vector. Now, it has a wind blowing at 28 meters per second to the southwest. So like I said, that is going to be a 45-degree angle. So I'm going to go in this direction. And it is 28 meters per second. I'm honestly not positive how long to make that vector. But if one of these major boxes is 25 and 25, then this one's going to be 25 root 2. I'm going to do that on my calculator real quick. And that's 35. So I've drawn it a little bit long. I might erase some of that just because I did my math and figured that out. That wouldn't be, these are representations. So we'll get to some more specifics. But for now, I'm going to draw it about that long, and we're going to kind of settle on that. What is the total velocity of the plane as seen from the ground? So this is, again, a point of reference. As the plane is going from the ground and you look up and you look at it, what is it actually doing? So maybe their instrumentation, they've got more sophisticated instrumentation than this, but maybe their instrumentation says that they're going 100 meters per second, or 100 meters per second to the north. Whereas you look at it and you're like, well, not really, because this is blowing it off course, and it's cutting into it, right? If the plane is flying this way and the wind is blowing this way, it's going to be making it a total of this because the wind is blowing it off course. So my resultant vector now looks like this. That's what it would look like from the ground. They think they're going 100 meters per second north. Not really, their instrumentation is better, but that's the deal. And we've got 28 meters per second going this way. Well, that's slowing them down and is pushing them a little bit off course. And so this is our resultant vector. And so that's what we're looking for. That's the question is asking point of reference. From the ground, what does it look like it's doing? Okay, well, unfortunately, we don't have a right triangle. And so we're maybe going to have to do some finagling to figure some of this out. And the way we're going to do that is going back to what I was starting with a second ago, this 28 meters per second. So it is a 45-degree angle, right? So I'm just going to come over here and draw it. So if this is our 28 meters per second, then what is this part and what is this part of it? We have to break it down to components. And because it is 45 degrees, we know that these are congruent to each other. This is a 45, 45, 90 triangle. And so therefore, this is going to be 28 divided by the square root of 2. Now, I relied on my geometry to figure that out, but we're going to talk about that with trigonometry as well. By my geometry method, I'm getting 19.8. Let's talk about it in terms of trig, because that's really what we will do more frequently in this class. Like I said a minute ago, we know this is a 45 degree. And so if that is a 45 degree, then we can think of it in terms of sine or cosine. Let's just do sine. We could say the sine of the 45 degree angle is opposite over hypotenuse. And so to solve for x, I'm going to, my calculator, I'm going to take 28 times sine 45. And I also get 19.8. Now, make sure your calculator is in degree mode when you do that, because it was 45 degrees we were talking about. Okay, so each of those legs is 19.8. Okay, that's important because what we can now do is say that from like here to here is 19.8. And from here to here is 19.8. So each of these pieces is 19.8. And so it's essentially, let's now kind of bring this down to the outer triangle. So I know that this is 19.8 from here to here. And then from here to here, well, what's 100 minus 19.8? 80.2. Okay, do you see how I'm looking at this resultant now? I'm going to change my color. So now I'm looking at this resultant triangle. And I have, if I'm going to do Pythagorean theorem, then I have a 19.8 here, and I have an 80.2 here. And then I'm going to find my resultant from there. And so I get a total of, I'm going to call this R. I had called it C up here. I'm going to call it R. My resultant vector is 82.6 meters per second. And I do need to find my direction, but at least I have my distance here. I will also say, in previous years, I think I've done this a different way. So that is just to say that there's always more than one way of looking at a problem. Okay, but I get 82.6 for my resultant distance. I also need to talk about what is the angle. And so I think just like on the previous example, I'm going to stick with this angle here, and I can say it's west of north. So that angle, I'm going to stick with, well, I can do any of my operations. I might stick with tangent. I don't know why. I'm just going to stick with tangent. So I'm going to say tangent, inverse tangent of theta is opposite over adjacent. That was 19.8 over 80.2. And I'm going to do that in my calculator. And I'm getting 13.9 for my theta. And so we could say that the answer to this question is the resultant vector is 82.6 meters per second at 13.9 degrees west of north.